we get really nice results. Even if I move totally away here from the image, we can just see we get this really nice relative depth in the image. We can see the details in the lamp, and also here at the light candles, and on the table, just the table in general, and so on. So this is really nice details that we get in our depth map. Hey guys, and welcome to a new video in this computer vision and deep learning tutorial. In this video here, we're going to do monocular depth estimation with the MiDaS Neural Networks. So in one of the previous videos, we already did this with monocular depth estimation with the version 2.1 of MiDaS, but they've now made new models with version 3 using some of the newest state-of-the-art transformer neural network architectures and so on. So we'll go over that in this video here. I'm going to show you how we can download the models, import them with pytorch, and how we can run it on the GPU to get better speed and performance. But first of all, remember to join Discord server. I'll link to it down in the description here. You can join the channel, shadows about computer vision, deep learning, AI, and so on. You can always become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. Also, if you have some problems in your own projects and applications, I can also help you out and give you some guidance if you're a member of the channel. So thank you guys. So first of all, here we're going to start at the MiDaS GitHub repository here. So here we can just see like all the weights here that they have, the output, the mobile, all the different kind of models that they have. But if we just scroll down here to the description, we can see that here we have towards robust monocular depth estimation, where they're mixing different kind of data sets for zero-shot cross data set transfer. So they're using different kind of data sets, combining them, and then they're actually training the model so we can do monocular depth estimation and have a really robust model. Because when we only have a monocular camera, we don't have any information about the depth in the image if we're just talking about the camera or like the single frame. And then they use actually like stereo vision images from different kind of data sets, also data sets where they have labeled the ground truth depth labels with lidar, like stereo vision, structure of light cameras, RGB cameras, and so on. So they have mixed all the different kind of data sets, and then they've trained this model here, the MiDaS model, to do monocular depth estimation. So you can just use a single camera, use a webcam, and then you can actually like get relative depth information in your image without using like stereo vision, any lidar scanners, or any other different kind of laser scanners where you get depth information. But here we can see that this repository contains code to compute depth from a single image, and we can even go in here and see the paper that they published. So here we can just see that they're now using vision transformers for dense prediction. So previously, when they've used the MiDaS version 2.1, they actually just used convolutional neural networks. But now we have these state-of-the-art models where we're talking about like transformers, how we can use transformers in vision and so on. So first of all, transformers were used for natural language processing, but now we can use them for vision as well. We're going to cover transformers more in details, like how transformers works and also how the architecture actually is, because it's really important. It's state of the art. So we're going to cover that in other videos here on the channel. So make sure to subscribe and also hit the bell notification so you will get a notification when I upload new videos about deep learning, computer vision, AI, and so on. But here we can see that MiDaS was trained on 10 different kind of data sets, where we can see with multi-object optimization, the original model was trained on 5 data sets. And then we can see some different kind of like change logs here. So here in November 2020, they released the MiDaS version 2.1, which was trained on 10 data sets, and they were still using old school or like old fashioned like convolutional neural networks to do image processing or like do deep learning for computer vision tasks. But here they released version 3.0 of MiDaS in April 2021. And here we see the new models are now based on dense prediction transformers and are on average 21% more accurate than the version 2.1 MiDaS model, which was the convolutional model. Then we can actually just go in here, get the additional models, and we can download them here if we want to import them from pytorch, or if you just want to like import them into opencv, for example. I have videos about that here on the channel, how we can actually like deploy our models, both our YOLO models, our custom models here, like for example this model here from MiDaS, how we can deploy that with opencv and so on. But this video here, we're going to do it with pytorch. We don't need to download the models here. It will take care of that in the code. So if you have internet access, it will download the weights here and also the models here when we actually just run the program later on, as I'm going to show you. But here we can see we have these different kind of models. We have both a mono depth, but we can also do segmentation with the MiDaS model here. So we can actually like segmentate out different kind of objects in the scene if you choose these models down here. We can also set up the requirements here. So it uses TIM. So often we already have PyTorch installed, opencv, but we also need this TIM here to be able to run these MiDaS models. If you just want some example code here, we can just go in, download the repository here from MiDaS, and then we can just go in and run the monodepth.py and also the segmentation here, and then it'll actually just run that. We need to place our input images in the input folder, and also and then we'll get out the output in the output folders, and so on. So if you just want to run examples on images, you can just go in and follow this guide here. But this video here, we're going to open up the webcam with opencv, combine it with pytorch, load in them models, and then do depth estimation on live webcam feed. We can also see we have some different kind of like additional models down here, which is fine-tuned on the Kitty dataset and also the NYU dataset. So if you want that, you can go in and take those models instead. But we're just going to go with these models here. We will download them throughout in the code when we're actually like loading our models with pytorch. So we're now doing this Visual Studio Code here, and I'm going to go through the code here where we're actually like first of all loading in our models. We open up our video cam web feed with opencv. We pass the images through our model, and then I'll show you how we can get the output. And then at the end of the video, I'm going to show you how we can actually like display our outputs that we get from the neural networks. First of all, we need to import our modules here. So we have opencv, we're going to import also torch here. So we're going to import pytorch. I have videos about how we can install and download pytorch to our computer, and also basically just go into pytorch website, go through the installation process, and you can then choose GPU support. You just get a couple of commands, you pass them into your terminal or your command prompt, and they will install and download pytorch with GPU support. We're also going to import time, so we can time how many frames per second do we get when we run this model here on a GPU. So in this video here, I'm just going to use a 1060 GPU from NVIDIA. Then we're also going to import NumPy here as NP. Down here, these lines of code, we're actually just going to specify which models do we actually like, or like what models do we want to try to download. So when we're actually specifying these models here, we just go down here and use pytorch to load in the models. It will just go in, download the model to our computer, and then load it into this MiDaS variable or MiDaS object here that we're going to create. So basically here, you just need to specify or like comment in the model that you want to run. I'm going to show you all three examples so we can see both the accuracy and also the inference speed. So we see we have the large model here, which is based on this dense prediction transformers, both the large model and the hybrid. And then we have the MiDaS small model here, which is still the convolutional network. So we already did an example with the MiDaS small model earlier here on this channel. So here with the large model, we get the highest accuracy, but we also have the lowest inference speed. We get medium accuracy here with the hybrid model, but we also have a medium inference speed. If we want to deploy our models on like mobile devices or something like that, or like some low budget computers, we can go with the MiDaS small model here. We'll still get pretty good accuracy, but the accuracy is lower than the two other models. And then we have the highest inference speed here with the MiDaS small model. So basically here, we're just going to go with the small model first of all. Then we're going to use pytorch. We just call torch.hop.load. We specify here the directory where we actually like have all these things. So this is exactly just the GitHub repository that I showed you on the website, the MiDaS GitHub repository. And then we just specify the model type that we want to load in here from GitHub. Then we can move the model to GPU if it's available. So here we just set the device equal to CUDA if it's available. So we just go in here and check if torch.cuda is available, and if it's available, we set the device here to CUDA. And if we don't have GPU support or we don't have a GPU, it will just set the device here to the CPU. We'll get a lot lower inference speed, but it can still work out. You can still test it out and see the results just to play around with it. And again, all the code here from these videos that I have will be in the GitHub link down in the description. You can just go into my GitHub, copy paste the code, run the programs or like run the scripts here on your own computer and test it out and play around with it. So here we're just going to have our model here. We're going to set it to our device. So we're just going to put it on our device, and then we're just going to evaluate our model down here. So now we basically have loaded in our model, and we also put our model up on the GPU. So now we're able to do inference on the GPU with our model here. So we also need to load some transformers to be able to resize and normalize the images. So we're going to load in the images, then we're going to like pre-process the images so we can actually pass them through the neural network. So we need the same input format every time, because that is how the model is trained. So here we can just go in again to the GitHub repositories, and then we can just load the different kind of transforms that we need. We're just going to load them into this variable MiDaS transforms. And if we specify the model type here as DPT large, if we're using the large model or the hybrid model, we want to use this transforms DPT transforms, because then it is based on transformers and we have a different kind of input format. If we don't specify the large model or the hybrid model, we're going to use the small model, and then we just go in here and use the small transform from the transformers MiDaS here that we created. So now we actually just have to transform here that we can then use or like apply to our images later on after we read them in from our webcam. So now we're going to use opencv to open up a video capture. We just specified the index here of our camera. So we have our capture, and as long as our capture is open, we're just going to run inside this while loop. At the bottom here, we're going to just have an if statement checking if we hit escape on our keyboard, we will terminate, we will jump out of the while loop and terminate our program, and then we're going to release our webcam so we're able to run the program later on again. But if you just go up here, we're just going to read in, first of all, we're going to read in an image from our webcam. We're going to store the image in this im variable. Then we're going to start a timer so we can actually time how long it takes to pass our image through the neural network, do inference on the image, and then also get the outputs, and then we're going to display it. First of all, here when we load in the images from opencv, it is in BGR format, and then we need to convert that to RGB, because that is the format that MiDaS is using when we pass our images through the neural network. So here we're going to apply the input transforms that we just specified up here at the top. So basically we're just going to transform our image, and then we're just going to put it onto our device as well. So now we both have our input batch here of our image, and we also have our model on the GPU. We have our image on the GPU, and then we're actually just going to pass our image through our model on the GPU to do the processing. Now we can go down and actually do a prediction and resize it back again to the original solution. So now we have converted it to the input batch here to the neural network. Then we do prediction, and then we resize it so we can actually display the output later on again. So here we are just going to get the prediction. First of all, we're going to use with torch no grad. So basically here we're just telling torch that we're actually doing inference now. We're not doing any training, so we don't want to have any gradients when we're actually taking this step here in our neural network and doing a forward pass. So here we have our prediction. We just have our model MiDaS, and then we actually just pass in our input batch here, or like an input image, into our model, and then the output from our model would be stored in this prediction variable. So down here we can go down and resize it to the original solution. We're just going to use this torch.nn functional, and then we're going to interpolate our prediction, or like our output. First of all, we're going to unsqueeze it, and then we're going to shape it here, or like resize it. So we're going to change the size here to the original image size that we load in from opencv, because when we applied this transformation here up at the top, we actually like resized our image and also normalized the image. So we want to convert that back again to the original solution so we can display it. Then we're going to use the bicubic mode here for the interpolation process, and then we're going to specify line corners here equal to false. And then here then we're just going to squeeze our prediction so we actually like get the correct format out. So we actually like get an image out instead of just like an array here. So we're going to squeeze our prediction. Then down here we have our depth map. It is still on the GPU. So basically here we have our prediction. Then we can actually just go in, take the prediction, convert it to our CPU again. So we take it down from the GPU to the CPU so we can do post-processing on the results. And then we're basically just going to convert that result. So we have our prediction on the CPU. So this is still a tensor. So we're going to convert tensor from pytorch to a numpy array. And then we just do it in this way here. And then we actually have our depth map here with all the values that we have. So basically here we just have a matrix with all the depth values in it. And then we can just display that with opencv when we're using numpy arrays. But first of all here, we'll just get some values here that we can't really display because we're just going to get relative depth values. So first of all here, before we actually displaying our results, we're going to use opencv's function here to normalize our image, or like our depth map, and we're just going to normalize it with min-max normalization. So basically we're just having the lowest values to be 0 and the largest values to be 1, and then we're just normalizing between 0 and 1 here. So this is our depth map. We will have values between 0 and 1 corresponding to the relative depth in the image. We're going to end our timer, calculate the number of frames per second. Then we're going to convert our color image back here from RGB to BGR, so we can then display it with opencv. Then here we're going to apply a color map on top of it, so we actually get the inverse depth, so we can actually just display the colors of the different kind of like depth in the image, instead of we just have white and black pixels or like gray pixels. So we just have like one intensity for displaying the depth in the image. Then we can actually like create this color depth map here. So again, we have a normalized image. So first of all, we're going to multiply it by 255 because we want to get values between 0 and 255 when we're applying this color map here to the depth. Then we're just going to specify that we want to use an unsigned 8-bit integer as the data type. So now we're just converted our depth map to color values instead, or like values between 0 and 255. And then we're just going to apply a color map, and the color map that we're going to use is called magma. And then you're going to see what it actually does when we apply it. It is actually just specifying or like applying colors to our depth map, so we can better, or like we can visualize the depth better in our image. Then we're just going to apply our color map here to our depth map, store it and in this depth map variable. And then now we actually have everything. We have loaded in our model, we've passed the image through the model, and then now we have the result here in the depth map. Then we can just go down, put out the text, so the number of frames per second that we get. We're going to show the original image, and then we're also going to show the depth map. So we're going to show both of them so we can see what is actually going on, what are we able to detect the depth to in our image. Again, we have an if statement here checking if we hit escape on our keyboard, and if we do, we just terminate the program and release our webcam. So now we're going to run the different kind of models here that we have. So I'll just start with a small model here. We're going to run a program, open up the video capture and see the results. So after this one here, we're going to test the hybrid model and also the large model, so we can see and compare the different kind of methods here. But here we can see to the right, we get the depth map with all this like magma color map that we applied. We get around 17 frames per second. We can see when I'm moving around here, it's pretty stable, pretty robust. We can see that we're actually estimating pretty nice depth. So my hand here, like the brighter the color is, the closer it is to the camera. So these are relative depth values that we get out. And we can even see if I'm moving further back here, we can see we get some more details here in the background. We can see if I'm moving my arms forward, we get this nice relative depth in the image. And even if I move totally away, we can see we get a lot of details in the background. So I'll just move away here. So we can see we basically just get all these different kind of like features here, like at the like TV, the couch, and so on. So we actually like have really nice depth precision, even though we're only running this convolutional model or like the version 2.1. So when we're going to run the other models here, we will get better results, and also we'll get better accuracy, but we'll also get like lower inference speed. So now we're going to use the transformer based models. We're going to go with hybrid one. Again, if you just run this code here, it will download all the weight files and the models to your computer as well. It will download it once, and then after that it will just use it from the cache. So it won't install it or like download it every time you run the program. It will download it once, and then it's just going to use it from the cache when you run it later on again. So here we can see now we get 4 frames per second. We're using the hybrid model. We can see we get a much more accurate, like way more accuracy here in the depth map to the right. We get way more details. It's just way sharper here for the depth estimation. But again, the inference speed is really low. Even though we're running on a GPU, we only have 4 frames per second, but we can see the depth here is really nice. If I move away from the camera again, and we can just see the details, like for example, the candles here at the table in the background, we get really nice results. Even if I move totally away here from the image, we can just see we get this really nice relative depth in the image. We can see the details in the lamp, and also here at the light candles and on the table, just the table in general, and so on. So this is really nice details that we get in our depth map. Here I'm just sitting in front of the camera, so I'm taking most of the attention in the image, and then it is actually just calculating the depth based on that. But we can see here my hands, they're really bright here now. The further I move away, like the darker they will be. So this is actually really nice. The last example here that I'm going to show is the large model. So again, we just get higher and higher accuracy, but our inference speed just is just way slower. So either you need a better GPU, or if you don't want to run it in real time, you just want to have a depth map, you should definitely just go with a large model where you get the highest accuracy if you don't care about inference speed. If you want to run it on some lower budget hardware and you don't really care about like accuracy that much, you just want some real-time application, definitely go with the small model. As you can see, you get really nice results, but you also have you also have a really fast model when you're using the version 2.1. Again, here we get some really nice details. It's really sharp depth map, so we can see like the hair here is it's just really sharp here when we're talking about the depth. If I move my hands up here in the front, we can see we still get these nice details even when I move them back and forth. And if I move out of frame here again, we can see all the details in the background. So here with the large model, we can actually see we get more levels, we get more details, like layer by layer in the image. So it's actually better to predict the depth in the image, like the relative depth in the image, layer by layer. So it actually tries to estimate the depth to all these different kind of objects in the scene. Again, we get these nice, really nice details here at the light candles in the background. We can even see them still here, even though I'm taking most of the attention here in the foreground. So these are really nice models. It can be used for a lot of different kind of things. This is state of the art within monocular depth estimation with deep learning. If you don't have like stereo vision and so on, you will still need to convert your relative depth values here to some real world depth values. But I've also made videos about that here on the channel. So thank you guys for watching this video here, and remember the subscribe button and bell notification on the video here. And also like this video here if you like the content and you want more in the future. It just really helps me and the YouTube channel out in a massive way. I'm currently also doing this computer vision tutorial where we're talking about basic image operations, camera calibrations, stereo vision to get depth information in our image, and also in our environment, how we can use stereo vision to create point clouds. We've even created point clouds with these depth maps here. We're going to cover that more in the future as well. But if you're interested in that computer vision tutorial, I'll link to it up here, or else I'll see you next video, guys. Bye for now.